things. So, is it okay? Oh. Yeah, so let me share the overall training stages so that the next slide will be clear. So first, we have an English foundation model. Let's say it's a Mistral 7B. And then we do a continued pre-training. So we have a huge amount of internet data, and we are focusing on Japanese, our language of interest. And we continue the pre-training of this model so that the model can perform better on Japanese task. So we evaluate to know that if the pre-training is working well or not. We evaluate with a framework called Language Model Evaluation Harness. So it's a benchmark, and if you run your model against this framework, you will get some score. So you can compare the score with the score of other model. It's similar like with the benchmarking app that you use for phone or something else. And then that's the Rakuten AI 7B. So we continued with the supervised fine-tuning, or sometimes people call instruction tuning. So for this one, we want to make the model doing good for a specific task. So task-oriented, and then we aim to have this model to be good at as many tasks as possible. So we collect the fine-tuning data for that task and gather it into one data set that we call fine-tuning data. And it's a moderate amount. It's much smaller than the data used for pre-training because it's focused for fine-tuning a task so that the model can do things. And to evaluate it, we also use the same framework or an evaluation for the task, other task in particular. And that's the Rakuten 7B instruct. And then we can also further improve the model by doing some alignment fine-tuning. In this case, we use reinforcement learning by human feedback, RLHF, and this one, it's a bit different. We use a small amount of chat data, and then the data is positive and negative examples. And to evaluate this, we can evaluate with human or a much larger LLM. So if you're looking for a model that you can talk to, like chat, the Rakuten AI 7B chat is the best choice. So first, before we fire up any GPU, let's discuss like what kind of model we want to train. That's we call architecture. Like the simplest things about architecture is like we want to train a small model or a big model. I put this analogy in what we call a league, like a boxing. So there are like a lightweight league, and let's say it's a model about 7 billion parameters or smaller. They have a faster responses. They are more cost efficient because you can run it with one A100, H100 GPU. And then, yeah. And then there is a heavyweight model that is much bigger. There are like 70 plus billion. And for example, like Llama 3 is 405 billion parameters. And they have slower responses, but they tend to be better at answering questions and more accurate. But these are resource intensive, like the Llama 405 billion, you need a 2 DJX box just to host it, for example. For this time, we choose a lightweight category. So we're training a 7 billion model. And then after choosing the size of the model, there is something else that we need to look in the architecture, which is a tokenization. So what is a tokenization? An LLM will process the input in the terms of token, in the level of token granularity. But the input is a text sequence. So what I mean by splitting it into a token, if I have this sentence, I give you an example in Japanese, Yokoso Rakuten Ichiba. So it's a welcome to Rakuten Ichiba. Ichiba is our e-commerce platform. So the model will split into, for example, this one is into 5 tokens. So we see here one token has 2 Japanese characters and sometimes have 1. But in different model, in different tokenization scheme, we can have one token split it into like only have 1 Japanese character. So the sequence is longer. And probably in some cases, you can have 1 character, like this time is a kanji character, split it into 2 tokens. So 1 tokens contain like less than 1 character. So it becomes even more longer. Why this token becomes splitted? Because the tokenization algorithm has a byte fallback. So if we represent the token with UTF-8, it will be splitted on the byte. So that's why 1 character can become 2 tokens, because the token is not available for that character. So this is the problem if we want to process Chinese data, Chinese, Japanese, Korean data for an English-focused language model. And most of the language model that is available today mostly are focused on English. So this is also one of our motivation why we want to train a Japanese language model and open source it so the community can use it. So I have also a question, like, given that the model will generate everything in the same interval, 1 token, 1 token, 1 token, which one is the fastest to decode? So of course the shortest one, right? But can we just put everything into 1 token? That one also cannot, because we will have an infinite possibility for the token to be made. And we have a limited amount of token that we need to set, because then we have limited memory and computing rack. So let's look at the typical LLM pricing table. The price of LLM is measured by tokens. So for example, this is the name of the model, and then the price is how many dollars per 1 million tokens. So it's counted in token. If we look at this example again, which one is the cheapest? So the shortest one is the cheapest. So we can define that improving tokenizer efficiency is like we want to add as many characters in 1 token, like Rakuten here become 1 token instead of 2 tokens, or maybe like 4 tokens as the bad example before, by still maintaining token usability in other contexts. So the token can be used for other words that also use the same character. So we design a more efficient tokenizer. We have compared it with Mistral model. So Mistral has a character per token below 1. So when you process Chinese, Japanese, Korean data with Mistral, you will see that some of your Chinese character, Japanese character, is split into 2. So we can also compare it with ELIZA Fast. The ELIZA is a Japanese model focused on Japanese language. So it has a 1.33. And there is also Swallow, which is a bilingual model, 1.4. And we have our character per token up to 1.62. So we are more efficient. We compare the English one, and it performs almost the same. But for Japanese, we are much better than the model focused on Japanese. So we can represent Japanese text more efficiently than Swallow by 15%. So if we look again at this example, ChatGPT here represents this sentence into 11 tokens. And Mistral here represents this sentence into 9 tokens, while our model represents this sentence into 5 tokens. So it's generated faster, and if we count cost per token, it will be cheaper to represent the same sentence. And let's talk about preparing data. Now that we decide the size of the LLM and the tokenization scheme suited for Japanese, and what about the data? Let's say we have a multiple text source. We get from Wikipedia, we get from other sources, and maybe we have other data. We scrape and things. We combine both of them and do many things. like formatting. Maybe some of them come in XML, some of them come in JSON, some of them come in plain text. So, and then cleaning, maybe some of them is just a new line, a carry HV turn, and we need to clean it. And then there's also language detection. If you're interested in a specific language, like you only want Japanese, then you do a language detection on it. There's also quality filter, depending on what kind of quality that you want, what kind of specific properties that you want with the data, the duplication, and then we can also sort downsizing it by the text quality. So let's say if you have some numbers defining the text quality, then you can sort it and then take the top several million. And I won't tell one by one of this because it will be too many, but I will tell the most important part is the duplication. Because you don't want the same data, the same sequence repeated. And yeah, just do the duplication, as many other papers also concluded. And then we start training it. So if we want to know if our training is good or not, we run evaluation. And as I mentioned before, I take this picture from our press release. We run language model evaluation harness, and we get a score. So we run the same evaluation to the other model. In this case, it's the Japanese model. And we are better than the model during May by 3 points. So this is the best model when it is released for Japanese data. And then we also compare with other Japanese model. We are also having some 4 points better than the best model there for English. So in addition to be good on Japanese, our model can also do English. And there's also another benchmark there that compare our model with the model from Tokyo Institute of Technology, from Google Gemma, Renan Ekomata, Cyber Agent, ELIZA, and Tokyo University. So as of 30 March 2024, this is the performance of our model. And this is comparing the model with the same amount of parameter. But we also see there are some models that are bigger than our model. So we also evaluate it. So we can be better than the stable LM instruct beta 70 billion. And there is like some small gap with the swallow 70 billion. So our 7 billion model can chase the performance of 70 billion model if we focus on the fine-tuning and alignment, as it will be explained later. And then, yeah, there's also some room of improvement with the Gemini Pro and GPT-4. So, okay, now we get the number. But eventually, we will use our model to do chat, to do a meaningful task, right? It's just a number. So we want to see how our LLM can perform in many different aspects. For example, we ask it to do writing, to role play as someone, like as something, and then information extraction, like summarization, reasoning, math skills, coding skills, STEM knowledge, humanities knowledge, and also translation, and many more. So here, Rakuten AI 7B is assuming the role of a concierge to reply an art travel review. So there is a website to book a hotel. And usually in the hotel page, there are some reviews to the hotel. And we assume here that the model is a concierge that want to reply to the review. So I ask here, assuming you a concierge of the hotel and your name is Taro, please write a reply to the following review written by Alice. And the review is in Japanese. And the review is like, yeah, the weather is bad, but it's okay because the hotel is close to the station, and then the time to eat in the restaurant inside the hotel is too short. And so maybe you can improve on that, something like that. And then the assistant reply, I'm glad to hear that you enjoyed your stay at our hotel despite the bad weather. And it addressed the concern that the limited dining hours at our in-house restaurant. And then it closed with the, we hope to see you again in the future. It's proper, but the review is in Japanese. We want to reply in Japanese, right? So we ask it to localize the response to Japanese. And it can also reply to Japanese. So the model is bilingual. It can be good on English and it can be good also in Japanese. And we also do a benchmark on the empty bench Japanese. So this is more focused on the chat capability more than the language model evaluation harness. So it has many aspects like humanities, knowledge extraction, coding, writing, STEM, role play, as I showed the example before, reasoning, and also math. So the model is good at humanities and STEM and also role play, but the model is lacking in math and coding here. And to compare it with the state-of-the-art model at that time, we supersedes the model, which is a swallow model, and by several points here. But if we look at the GPT-4, there are still some room for improvement, especially on the math and coding here. So that's about the Rakuten AI 7B. And please try. It's open source and the license is Apache 2, so you can use it freely. And it's available on Hugging Face. So you can also check more details at our technical report. It's in archive. And that's all from me. Thanks.
Well, I think we have maybe a time for a question if there are any. If there is none, it's fine, but don't be shy. Okay, none. Oh, yeah.
Yes. Translation task.
Like how accurate is it compared to spoken Japanese or like spoken English?
So yeah, I probably qualified to answer this question. So it's lacking behind the GPT-4. It can produce decent translations, understandable for certain domains, not for all. So the answer would be here. If you want to try it, see how it performs for your use case. If it works, it's great. If it doesn't work, you might find an alternative or do some fine tuning after that. So it's decent. It's not perfect. Yeah.
Like can if ego has an output, if possible.
I think the good thing with this translation model based on LLM is like you can tell it in the prompt and it will somehow do what you ask or somehow don't do what you ask. Like, so, and you also can translate more than one sentence at a time, for example. Like the level is it's kind of flexible. So if it doesn't do as you ask it to be polite, but it's not polite, then the next session will help you how to improve it. Yes?
One first, sorry. Because there's also an online session, right? Also, maybe can speak to the. Yeah.
So the data pre-processing part, I mean, do you have any project which you're trying to open source or something which can automate most of the data pre-processing part? Or is it mostly manual?
Oh, we open source the model, not the data pre-processing. But I think if you're looking for a data pre-processing, you can follow some projects that are open source. For English, you can use Dolma. I recommend that because it's quite good data and they report a lot of details in the filtering. And they can have a good model with a good MMLU. For Japanese, there are also LLM JP. They share their pipeline in the GitHub also.
Okay, thank you.
I wanted to know what were the resources like during the training? For example, what GPU did you use and how long did it take for you to train? Like if you can share.
Well, it's a hard question. It's a secret.
It's a good question, but it's a hard question.
We understand most of the power or capabilities of recent large language models come from the RLHF part. So in your experience, what was the most challenging part in designing the RLHF? You mentioned you use both LLMs as well as human feedback to train the RLHF part. So could you share some experience from that?
Do you mean like how much the improvement comes? Is it from the
and what is the
pre-training?
process or what are the things you did to improve? Because we understand pre-training is one component, but the thing which gives most capabilities is the RHF part. So what are these important things an ideal model, if you want to achieve these kind of capabilities, should have?
You want to answer?
Yeah, I think we can talk about it in the next talk, actually, a little bit, cover it. You can ask your question there as well and see if you have any after. Yeah.
So you mentioned that you used also some data from yourself and that you also scraped data. How did you make sure that all the data that you used was legal to use?
Oh, no, this data is from ClueWeb.
So it's an openly available data source that you used?
Yes.
So I guess the interesting thing here is in a bilingual model, I guess there is two sets of data. I'm just wondering, do you ever see that there is a 1 + 1 is greater than 2 synergy in the sense that using additional Japanese data set actually helps if we are using it as an English only AI, does it actually improve its performance or does it actually deteriorate in performance?
So we found that multilinguality improve each language, but if we take a Mistral model, English model, and we just fine tune it with Japanese, it will forget English. So the English score will decrease and it will be good on Japanese. So the challenge here is to have a balance between English and Japanese, how you can make it good in Japanese, but not losing English performance that much.
So regards to AI safety, I think there are some traction, people are looking at like how to make a bomb, right? When they solicit this kind of responses, is there anything that Rakuten is doing to actually mitigate this kind of query?
So first, the data that we use is safe. We get it from ClueWeb, and all the filtering that needs to be done has to be done. And also, we can also improve it from the fine tuning also, like from RLHF. That's usually where you can patch the safety of the model.
I want to revert back to the question that this gentleman asked in regards to the quality of the translation. I didn't hear a conviction in you in terms of its performance. Can you elaborate a little bit more on that, please?
Could you repeat, please, question?
Yeah.
Elaborate on?
Pardon?
Elaborate on specific.
On the quality.
Right. So there are open benchmarks again to measure the quality of how translation works, right? And the benchmarks usually released by conferences or companies like Microsoft or Facebook who are interested in introducing translation and benchmarking. We are using Flores 200 benchmark and NTRX to measure quality of the translation. It's a news domain. So, and on that domain, we can basically reach a comparable level of performance with ChatGPT. But besides that, right, so if you want to evaluate it on maybe longer sentences, right, whole paragraphs, there is not a lot of benchmarks to do that, right? And if you're not specifically focusing on actually developing these benchmarks and running a really systematic evaluation on the translation quality, it would be hard to quantify what the translation quality would be, right? So one way to estimate it is to basically start translating sentences and ask people, well, whether you like it or not, right? That's one approach that you can take. But I can't really comment on the quality of translation, right? Without having a domain in mind, right? Without having what sort of sentences are we going to be translating it, whether it's going to be a formal, especially important for Japanese language, right? Whether it's we care about formal or informal translation and so on. Right? These things would be very hard to quantify at the moment.
Okay, I think we'll pause the Q&A for Johannes first. And a round of applause for Johannes, please. Okay, next we have Max. I'll let Max introduce himself. Setting up. So, reminder for those of you who just now was tapped in, right? Remember to collect that ticket to exit. Otherwise, you'll be a security guard for this evening. Yeah. So, to take note of that. And for those who may want to take this opportunity to check the ticket is still with you. Otherwise, you also will be the security guard. Sure. We'll have to check. Yeah. Okay. Yeah. Go ahead.
Okay. So I'm Max. I'm going to be talking about a part that is related to the second one that Johannes mentioned, which is some sort of fine-tuning. And in particular, I'm going to be talking about parameter-efficient fine-tuning because, well, I think when we endeavor on the quest of building our own LLM, or in general, if we're dealing with LLM, we really want to optimize resources that we use and want to squeeze everything we have from the GPUs we have, from the data we have, from the fine-tuning data we have, from human annotations that we have, a lot of squeezing. So I'm going to be talking about parameter-efficient fine-tuning. And parameter-efficient fine-tuning, in this case, we're not talking about optimizing GPU operations, right? We're talking about actually reducing the number of parameters that we're going to fine-tune in the model to make the model respond to specific questions and scenarios. Okay, so one prerequisite for this is that we've completed pre-training, right? We have a really decently pre-trained model that has seen a lot of data. And this is going to be important, and we're going to be, I'm going to show why it's going to be important at the end of the talk. Okay, so we're actually not interested in LLM itself, right? We can train as many LLMs as possible, but we're interested in solving specific problems, right? And these problems can be as easy as deciding whether a sentence is a positive or negative, right? Which is called sentiment analysis task, traditionally explored in academia. And you probably can do some useful stuff with it on social media to understand how people react to your products, right? And so on. Or you can go in details to solve basically emotional, to judge the emotional state of the people using some sort of classifiers like that. Or we can do the translation task, right? In this case, quite simple translation. Since it was raining yesterday, I watched a movie at home. And we want to utilize this kind of unified interface of so-called large language models to do all these tasks. But again, we're interested in specific tasks. And to enable LLM to do the specific tasks, we would need to have some sort of fine-tuning data. This fine-tuning data would look like this, right? Here we have basically instruction to indicate what we want. If we want to extract the sentiment from the following text, we have a text, input text. Maybe we have some sort of additional information that we condition our language model on. We can solve more complicated tasks like generating the code, right? Which would require to put you some sort of predefined code base into the model and ask complicated questions like rewrite, refactor the code, whatever it might mean. And we provide the answer that we expect. Now, we have additional formatting here. We have user to indicate that the request comes from a user. And we have assistants to indicate that the LLM answers after the assistant tag. So having a lot of this data, we basically can take our pre-trained LLM, expose this LLM to a lot of these examples, and see if it performs well. right? Using all this evaluation metrics that Johannes was talking about. Okay, let's say we want to go on this endeavor of fine-tuning Rakuten AI 7 billion. First question would be, well, what kind of resources do we need? And I'm going to be talking here not about the compute. Compute is probably the obvious resource, right? You'll have H100 card or A100 card. Your training is going to be fast. And I'm going to be talking about resources that are limited to RAM, to GPU RAM. So just to put a Rakuten AI 7 billion on the GPU and do inference with it, you would need about 14 GB of RAM, right? Without any quantization, here we have half precision model. Well, if you want to your model to process your input in a very accurate manner, you might do a full precision. You might put a full precision model in your GPU, right? Or you might want to combine and put two precision models on your GPU. The reason is small half precision models are a little bit faster because the GPU can compute half precision operations a little bit faster. But full precision give you a little bit less errors in computing the numbers. Now, for training, it's usually that we put all this 14 billion, occupy 14 GB and 28 GB at the same time to do a mixed precision training. That is very important when you train especially large models to stabilize the computations, numerical computations in the model, but also have a gain of fast computations when it matters using the half precision model. Besides that, you would need to store as well updates to see how to optimize the model, which are stored in full precision for each parameter of the model, which is as well 28 gigabytes of RAM. And if you're using some advanced optimizers, they would require about 56 gigabytes of RAM to store parameters related to optimization, which is first or second momentum for the gradient parameters. Okay, so, and looking at this, right, you can kind of imagine how much GPU RAM we need, right? It's at least 120 GB of RAM, and there is no GPU that can fit all these things at once at the moment. So if you look at the price list of the GPUs, they're expensive, right? Here I'm taking the price list from Lambda Labs. They are on the cheaper side. And just to train this model in a naive way, you would need to utilize the bolded GPUs here, right? Having multiple nodes, try to put it on the GPUs and see, like, you can imagine how much money you're going to spend. If you need to train the model for hours and hours, or if you need to fine-tune it for hours and hours, you're going to be spending maybe at least, it's going to be at least $5 per hour. Doing it in a naive way, right? But, well, we don't want to do it in a naive way. We want to do it in a parameter-efficient way. In this case, you would need to still store the model on the GPU, which you can do in half precision or even 8-bit precision, which still occupies 14 GB of RAM. But the idea here is let's try to fine-tune a really small number of parameters so that we can occupy our GPU not as heavily as if we were to fine-tune the whole model or to train the whole model. And roughly the estimates I would give here is we occupy a GB for optimizer states and half GB for the gradients. So that's kind of already manageable. That actually can probably fit on the free tier GPUs on Google Colab. And with this resources, you actually can fine-tune the model to do your task on just free GPU from Google Colab. And the method that allows this is called LoRa. This is the only method I'm going to cover for many reasons. First, it's been shown very efficient. And second, it doesn't change the architecture of your base model. So what happens here is that, well, our model is a combination of some linear transformations, some matrix multiplications, right? Sandwiched in between some nonlinear transformations like sigmoid, softmax functions, whatever it is, right? So for every linear transformation, we can create an additional path, which is in orange here. right, that transform our input vector into our output vector, right, somewhere in the model, in between of the model. And what we do, we keep our model parameters, pre-trained parameters, fixed. We don't change them, but we optimize on a small portion of these parameters that would approximate this linear transformation, but with the operation on a much lower rank. Here, R means rank, and we can some sort of initialize these parameters in some way so that they don't change the operations of our model initially. So it's important to kind of understand where the savings of the parameters coming from, right? So when we have our linear transformation of the size d, so we basically transform vector d to output vector d, we need to multiply this vector by this huge matrix, right? So, but this matrix can be approximated as a multiplication of two small matrices. And this is very important because the number of parameters that is required here is squared to the dimension of our input vectors and output vectors. Whereas in LoRa, we have a factor A, R, which is a rank of the matrix, that actually controls how many parameters you have for your fine-tuning. Now, this is important because that allows you to reduce the number of active parameters in the model that you need for fine-tuning by magnitudes. Like, instead of fine-tuning 100% of the parameters of the model, you only need to fine-tune, let's say, 0.2% of these parameters. And that's where the savings on GPUs are coming from. So another good and important thing about LoRa is that it doesn't change the model architecture of your base model. So having computed this shadow path of the transformation, you can take these matrices, small matrices, compute the full matrix, and sum it up with the original model. So without changing any architecture, you can actually do a full fine-tuning of the large model on a smaller consumer-grade GPU. And well, this is all math. This is not really important to understand probably. But basically, if you were to code this, it would involve a few changes, right, in your code as how you do the training. And you basically, if you're using Hugging Face Transformers library, you would add the config, LoRa config, and then get PEFT model, put the LoRa config there, and see how it performs. So let me take a step back here, and I actually want to demonstrate you how easy it is to fine-tune the model, and I hope by the end of the talk we'll have something that will be able to translate our text from English to Korean. So I'm taking Rakuten 7B here model. I'm using one GPU. What I have is Quadro RTX 6000 with 24 GB of memory. Well, let's load it. So in the meantime, that's the task I want my model to do, right? So I have a user token here, then I have an instruction translate to Korean, and then I have my example sentence, right? And I have an assistant token from which the model is supposed to generate the continuation of the text. Okay, the model is loaded. This is how my instruction looks like. Translate to Korean. Okay, what I'm doing here is I'm using my currently non-trained model to generate the answer to this question, just to showcase that it doesn't really work, right? So the model is not fine-tuned at the moment. Here, I'm initializing the LoRa config with a rank 8, which requires about 0.2% of all parameters to be fine-tuned. Here, I'm taking the open source data set, Facebook Flores dev split, to generate the training data for the task. So basically, I'm going to have instruction translate to Korean, then some English text, then the appropriate translation for Korean, to Korean. Okay, this data is processed. I'm going to launch the training. It's going to take a while, so I'm going to switch back to the presentation. But basically, you can see that the model is being trained, and it just requires 24 GB of VRAM. Okay, let's go back and talk about, well, maybe, right? Maybe I'm fooling around, right? And fine-tuning just 0.2% of model parameters doesn't work, right? Let's assess this kind of problem by giving real data to the models and try to fine-tune these models with LoRa, right? Here I'm going to be talking about existing research on LoRa fine-tuning. Here we have basically a task that gives you a schema of the database. You have a question, natural language question, that says, well, how many CFL teams are from your college? And the model is supposed to output the SQL to query this data. So here are the results of the experiments. Here's, we have some data set that we're using to fine-tune this data, and then we evaluate it on the validation set. Here we have full fine-tuning that requires a lot of trainable parameters, right? And this achieves a certain level of performance, so the higher the better. It's about 75, just below 75, 74. And we have different parameter-efficient fine-tuning methods, out of which LoRa stands out. And with magnitudes orders of lower number of parameters, it achieves a level of performance comparable to LoRa, to full fine-tuning, which is kind of impressive. We can also take a different task, right? Here, that's basically what I've shown, right? It's a fine-tuning for translation. Similar kind of things, except like here we're going to be talking about translation from Chinese to English and English to Chinese. Okay, I believe the model that is fine-tuned here is Llama 7B. And we can see that, again, fine-tuning reaches the same performance as LoRa fine-tuning. So actually, fine-tuning a small number of parameters, not a bad idea. At least we're safe on GPU. And probably we won't reach the top performance that we can do with a full fine-tuning, but we reach performance that is comparable. So what are the drawbacks of LoRa overall, right? So data scaling is ineffective for LoRa. So if we have a lot of data instances, so we won't have much gain if you train LoRa. So what happens here, we have two models, Llama 7B and Llama 70B, evaluated on different aspects like helpfulness, clarity, factuality, depth, and engagement. Now, dotted lines indicates training of fine-tuning this model with LoRa with less data, and solid lines indicate the fine-tuning of these models with a larger amount of data, right? And using LoRa fine-tuning. And you can kind of see that the lines, right, of the same color intersect. So scaling the data doesn't work well with LoRa. So, and probably there is a reason for that. And if we analyze how different LoRa fine-tuned model from original pre-trained model, we find out that actually fine-tuned model with LoRa rely heavily on your pre-trained model. Now, that suggests that having a really model that is well pre-trained at the beginning is really helpful if you want to do some sort of fine-tuning in a parameter-efficient way. So what happens here is that basically we compare full fine-tuning and LoRa fine-tuning. We compare the probability change for the first 5% of generated tokens and last 95% of generated tokens. The lower it is, the more similar it is to pre-trained model. Now, full fine-tuning changes the model quite a lot, whereas LoRa fine-tuning doesn't change the model quite a lot, at least for the last 95% of the tokens, but it changes a little bit the starting tokens. And it's one of the good analogy to think about it is that, well, your pre-trained LLM contains a lot of knowledge. So it's been trained on a lot of books, internet resources, right? And what LoRa does is just being a helpful librarian that points you to the right point of the knowledge within this library
and says, okay, here's the answer that you're looking for. That's one of the analogy how to think about it. Probably not necessarily a super accurate analogy, but it implies that it is very important to have a well pre-trained model that is exposed to a lot of information beforehand. Okay, so LoRa fine-tuning, if you're not yet convinced that LoRa fine-tuning is quite a good method to save your resources, it's been used in many different ways. For example, NVIDIA used it to create an embedding model that ranks top on the massive text embedding benchmark. Control LoRa by Stability AI is something that's been applied to image models. Mistral AI offers model customization, which is based on LoRa fine-tuning. And besides that, you can find a lot of LoRa models on Hugging Face, and you can create one yourself. So here's the end of my talk, but let's see if you have a model that is trained already. Here I'm going to input the same sentence. The training has finished. And let's see if it can translate it to Korean. Okay, yeah. It does output something. I'm not sure if it's correct, but whoever knows Korean, please verify. Okay, this is the end of my talk. If you have questions, feel free to shoot.
Does the base architecture change the way LoRa works? Like, for example, mixture of experts versus decoder only. Does it change the way LoRa, gives an output?
It does not necessarily change. It probably requires some code changes so that library supports how to insert itself into any linear transformation. But basically, if you have linear transformation, you can have a shadow path that decomposes this linear transformation, the low rank matrices, and you still can do LoRa. So in practice, you can apply it to MOE, you can apply it to whatever model that has some linear transformations.
Any specific reason for choosing MOE in this case, Rakuten 7B?
It's not MOE. It's not MOE. It's a decoder only.
Okay.
When you're asking the question, can I request that you all speak into the mic? Yeah, thanks.
So with regards to LoRa, I'm here.
Yeah.
So I guess there are also hyperparameters for LoRa, and I just want to see is there any intuition that you can recommend, or is this really like a sweep of hyperparameters and choose the best result?
So yeah, I think you would need to run evaluation. But for example, right, in this case, they were scaling this R factor quite a bit, and you see the performance basically varies. So I'm not sure what it means. Maybe for this task is enough, but for your specific task, you might need to actually fine-tune it and see what works best for you.
So I had a question regarding LoRa. In LoRa adaptation, are we just training the attention layer, or are we tuning the MLP layers as well, parameters in the MLP?
Okay, so it depends. I think if you want to achieve the highest level of performance, then you would need to do fine-tuning on all layers. If you want your model to retain some original knowledge without hurting model too much, you probably need to target something specifically. Right, you want to target maybe attention, only attention, right, without MLPs.
Okay, so I have a question, two questions actually. Like the first one is when we're fine tuning with LoRa, is the number of iteration proportional to the performance? And the second question is about if even after we did the LoRa training for whatever we could, but like the performance is still not good enough, is it better to just do some hyperparameter tuning, or do we just like combine LoRa with like other fine tuning methods like adapter, for example? Like, yeah, is it better to do it that way, or like, yeah,
right,
the other way?
So okay, I don't know the answer to your questions, right? So I can only guess. Basically, for sure, there is a correlation between number of iterations you spend on training a model and the performance. But at some point, it probably will saturate, right? And I think for LoRa, depends on your resources, right? So what's also good about LoRa, that if you have even a big model, if you have a decent GPU, you can fit a big batch of your data into them, right? Which increases your compute capacity. You process more data. In this sense, you probably need less iterations than the full fine-tuning to reach a better result. So basically, there is going to be some correlation, but there is going to be stagnation at some point. Now, okay, but if the performance is not good, would you want to try other methods? You probably want to try first increase the number of layers that you target with LoRa. If you were targeting only specific layers, that might help. But yeah, if your pre-trained model does not have enough knowledge to answer the question, then you probably need to either do full fine-tuning on your data, right? Or to find a better base model.
Hi, could I just check with you for converting the model from Rakuten continue pre-train to Rakuten instruct? Was it LoRa or was it full fine-tuning?
Well, that's a good question, but it's a secret.
Okay, then could I just have like...
Unfortunately, I can't expose the details of how exactly our model was trained.
Could I just check with you? Because for my intuition is that from CPT until instruction, tune, and then also DPO, right, or preference optimization, there will be some drops in performances and different types of evaluation data sets. So could you provide any kind of intuition on at each stage, were there any particular big drops that you had to account for, such as some code performance or anything like that? Thank you.
I think it's very hard. It's a question that is very hard to answer without knowing the settings that you're dealing with, right? Because, for example, just introducing the bad fine-tuning data would hurt your performance a lot, right? Maybe even mixing tasks might hurt your performance. Like, you can mix tasks like translating for traditional Chinese and translation to simplified Chinese, and you name them the same way, Chinese, right? Then your performance would drop because the task conflicting. I think it's really requires knowing your settings, right? What kind of data do you use, in what proportions, and whether the tasks are going to be conflicting. Yeah.
Right. We'll pause the Q&A for Max here first. I think maybe after the next talk, after that, you all can do the Q&A with Max again. So maybe a round of applause for Max, please. And may I invite Alberto to come and set up first? Right. A round of applause for Alberto, please. And go ahead.
Okay. Okay, so okay. Hello, everyone. So yeah, I'm Alberto Boncelas, and this part of the presentation will be improving large language model with preference optimization. And okay, so to see where we are in the pipeline, so far, like we have seen how the Rakuten model was built. Now Max can tell us how to do efficient supervised fine-tuning. And I will focus on the last part, the alignment on the model. And yeah, like I will explain how what is alignment, how it can be done like using this preference thing. So, well, to start with, here I put a screenshot of, if you go to Hugging Face, actually to the Rakuten chat model. So you can see how it can be logged. We have seen also in the notebook of Maxim how can we load the model, and then we can start like asking to perform tasks. So here, well, here there is a question in Japanese. Also, we have had to prepare Spanish omelette. But in this presentation, I will focus on the task of how to translate. So what I'm going to explain here, it could be used for other tasks, but as a use case, let's use the translation. So, okay, how can we do the translation? Just go to the model. We have, let's say we have this Japanese sentence, and we want to translate to English. So the same thing as we saw with Korean, like please translate this to English. We give it to the model, and we'll get some translation. So this model is trained on English and Japanese, and it will, let's say, it will answer something to this, to how to translate this. But we don't know, maybe what we expected from the translation, it was of something of higher quality, or we want, let's say, we want to translate in a very particular domain. Let's say we want to translate something in, go ahead. Sorry. So we want to translate something in the physics domain, or architecture, or biology, or something like that. So then in this case, we need to teach the model how to translate this particular domain. So if we want to improve, we want to improve the translation, what do we have to do? Fine tune. This is the first step. Like if we want to improve it, we give, in the case of machine translation, we will give parallel data, so a bunch of sentences in two languages with the same meaning. So in this case, if we translate from Japanese to English, so we give some sentences in the source in Japanese, let's say, target in English, compile everything we can, and give it to the model and start training. And then we can use LoRa and all these fancy things. So, okay, so far it's a bit of recap, like all the pipeline. If we want to improve, let's gather more data, give it to the model, and let's build a model that translates properly, that translates like very good sentences. So in the example that I was talking before, like we have this, like translate to English this, like this sentence is something like, could you send me the report today? And so we give it to the model, and it will try to find what are the most probable translation for this sentence. So this sentence is kind of polite. So let's say the most probable sentence is something like, could you please provide the report today? That would be like the most probable, the one that the model thinks is the best. But internally, like, it's searching for the possible translation. So another candidate, we have to retrieve more sentences, could be like the second most probable, like, would you mind sending the report today? Or something more, let's say, more plain English, like, can you send me the report today? More direct. Or it can be, hey, can you send me the report end of the day? So all these sentences have the same meaning as the source. So, okay, we can say they are correct, like we got all the data, and we build such a good model that translates things properly. But now, maybe depending on how we want to use this model, maybe we don't want such, let's say we don't want such a polite translation. We want something more in between. Let's say we would prefer if the model had said, can you send me the report today? Instead of, could you please provide me with the report today? So now the task, like, although the translation is good, now we want to be more specific. And so we don't need the model to provide a much better translation. We just need to, among all the translation that it can provide, somehow tell how we would like the translation to be. So this is what we call the alignment, which is make the LLM behave the same way that we expect or we want, or the end user wants. So, and actually in this case, like, because we are being like more specific with the model, like so far, if you see fine tuning, what we have done so far is telling the model how to do things. So, like either in the training data, or in the case of translation, this sentence has to be translated like this. This other sentence has to be translated like that. But now we want to be a bit more specific. So we would like to say, we would like to tell the model also what not to do. Like, please don't use these words. Please don't translate this way. Please be more polite or be less polite or be, I don't know, use this other vocabulary. So now the LLM alignment is a bit more specific. And now what our task, like once we have, because we have everything ready, now our task is to check what is the output of the model and then give a feedback to the model. So this is this kind of the loop, like there will be some user or annotator or someone in charge of adjusting the model so it behaves the way we want. So this is why I have this loop. The model will make sense, like will generate some translation, or depending on the task, they will generate some answers. And now we want to take this output and give somehow feedback to the model so it starts producing the answer or translation the way we want. Okay, so one step is like one thing is like, okay, we are going to give the feedback. Like, how are we going to provide the feedback? Well, one easy solution is just, okay, in the case of translation, we just need to take someone, an expert who knows, let's say, Japanese and English, sit down and start writing sentence. So this, for our task, we want this sentence to be translated exactly this way. And we generate, or we ask someone to start producing a lot of sentences, and then we give it back to the model. We could keep doing fine-tuning until the model is exactly whatever we want. The good thing of this is that it's highly customizable. Like, we can say exactly how things we would like to be translated. The bad thing is that actually someone has to sit down and do all the work. And this is time-consuming, and therefore this is expensive. So, okay, yeah, so effort, 5 stars, like very difficult. Okay, let's try to do something more simple. Post-edit the LLM output. Another thing we could do is ask the model to start translating or start or answer the question or the task that we want to do, and then once we have the answer, we indicate what is wrong. Like, oh, this word shouldn't have been said, or this conjugation should be different, or this word order should be different. So again, we have very fine-grained feedback. We are telling the model what is doing wrong and what we want it to do properly. And we could do the same, like provide it back to the model. But again, this is time-consuming. So it is a bit less time-consuming, it's a bit less of effort, like 4 stars. But so a person doesn't need to generate both source and target and everything from scratch. It's a bit more simple, but still someone has to sit down and write everything like we want, exactly this and exactly that. Okay, let's make something more simple. Scoring. Yeah, this is more simple. Again, we ask the model, please translate this, we get some output. And then we just need to score, it's not post-edit or anything. Like this translation is 10 out of 10, or 0 out of 10, or 5 out of 10. Yeah, very easy. Effort, 2 stars. Less expensive, less time-consuming. Yeah, easier. But here is the problem, and there are many words that they complain that this is not very stable because, like, to start with, you need very good you have to establish very good how to score things. Because first, different people will score things differently. Like the same translation, if you ask to one person or to another, one may say, oh, I think this is 6 out of 10, and another one 7 out of 10 or 5 out of 10. So usually there are disparities between what people think the quality should be. So it has to be very well established, and you have to, again, pay money to train a person to exactly know how to score things. But even if we do that, sometimes, because we want to, let's say, gather all the problems and summarize as a one score, this can be problematic. And in the case of translation, there are, for example, two main aspects that are typically are measured. And one is adequacy, and the other one is fluency. So in a translation, we want the meaning of the translation to be the same as the source, and at the same time, we want this the adequacy, and at the same time we want to be fluent. We want the translation to look like it has been produced by a person who actually knows the language. So here, for example, we have two aspects: adequacy and fluency. If both of them are high, then high score. Okay. Both of them are low, low score. Okay. But if someone is high, if some aspect is high and the other one is low, then it's like 5 out of 10, 0 out of 10. So, and this is only with two aspects. If we consider more things like it should be safer, or how well in domain the sentence, or the example we were looking, the politeness. So if you have so many aspects, somehow you have to summarize everything into a single score, and either you have a very well designed, and even so it's something that is difficult to measure. So, okay, effort too, easy, but still has these problems. Okay, something more simple. Deciding or choosing between alternatives. This is the approach, the least expensive approach, is the easiest one, effort one. We just need to give the sentence to translate to the LLM and ask for two candidates, two possible translations, or whatever the task you're using. So let's say we have two different translations, and we ask a annotator, a human, to decide between one or the other. So yeah, that one is easy. No need to write down anything. Just choose, like, I prefer one, or a translation A over translation B, or B or translation B over A. Very easy. The problem, I mean, it's not perfect. It has some problems, because the fact that one is better than the other doesn't mean that one is good and the other is bad. So what if both of the translations are good, are bad? What if, like I was saying before, like I want some kind of plain English, not too formal, not informal. Then what happens if we ask the LLM for translation, and one is too formal, the other one is too informal? Yeah, maybe one is better over the other, but it doesn't mean that it's exactly what you want. So it still has problems. Ideally, if you have a lot of different sentences, ideally, like you can get some intuition of what human would expect to have. And because this is effort 1 star, we can make like a lot of we can give like a lot of feedback easily and cheap. So I mean, this is the preference part. Like in the end, we end up having some triplets of data. So for fine-tuning, for the supervised fine-tuning, we have like pairs of sentence, source language, target language. Now we have 3. Source language sentence, a chosen translation, which is the one that the annotator preferred, and rejected translation, the one that is dispreferred, the one that is the loser. So actually, in some words, this is like the winner and loser alternative. And so once we have this triplet, this is what we want to give to the model and say, oh, this kind of sentence are preferred, so this promote that. In the ranking I saw before, in the ranking of sentences that the model can do, please promote this one, and please demote this other one, like penalize this one. So this, right here, like promote this and penalize this candidate, it will be somehow like doing this, like the ranking re-ranking the sentence. So yeah, let's say if our favorite translation would be like the third one, like, can you send me the report today? What we want to do is use this data to promote that one, and the one that is too polite or the one we don't like to demote and therefore make the model to behave the same way, like the same way we want. So typically this preference data, what the annotators have done, usually is used to build something called a reward model. So we could build a model that is some kind of classifier, some kind of model that will score our, like, given a prompt and an answer, it will give us how good this answer is aligned to what the human want. So by like maximizing the accepted score and minimizing the rejected score, like the rejected sentences, we can build this kind of model. And then when improving the LLM, we can influence this kind of ranking, this kind of which one is the most probable, with the signal of the reward model, with the reward score. And that way we see that, like, could you please provide the report today that it was in the top, so we push it a bit down, and we promote the other one. Can you send me the report today? And that's mainly it. There is, like, because this there are like people investigating these kind of things, and there are like new ways of doing this. There is also the direct preference optimization, which come from a paper that say that your LLM is also a reward model. Your large language model is secretly a reward model, something like this. And what they claim is that you don't need a separate reward model. You can just give the preference data to the LLM you are improving. And by keeping a non-aligned and aligned version, you can play with the ratio and still re-rank the sentences. And yeah, that's it for me. Like, now if there's any comment or anything, just let me know.
Questions? I think some of you also got questions for Johannes and Max as well, right?
My question is on the RLHF part. The main problems we see where LLM strip up is planning, or in cases like where we want to solve reasoning problems like you showed in the earlier supervised fine-tuning. What are the kind of applications that you see in where this Rakuten AI LLM is able to solve problems beyond translation, or much more harder problems from your experience? Where the RLHF really helps.
Like, which problems could be solved, or
yeah, in the applications that Rakuten is facing? What are where it's deployed live, or what are the kind of applications?
Another secret.
Yeah, because
yeah. Well, so I can generally speculate of what kind of data or what kind of domain would be useful to have in a preference optimization, and it would be something like safety. So basically saying, well, this is not a safe sentence, where you suggest some illegal activity, right? And you want your model not to generate those, right? Or indeed, like Alberto said, right, fine-tuning to a specific style of language, right? Where you just need to fix certain things. Like, model kind of know what to do, but it needs to be pushed a little bit to do the ranking right, so that it generates more fluent sentences in a more probable way.
And one more question is, I understand the data scale is secret, but if you say if 100 is the scale of data you do supervised fine-tuning and RLHF, what's the proportion that you allocate for RLHF or how do you distribute the effort?
So, okay, that's also an interesting question. I think the more fine-tuning data you have on a lot of different tasks, the better, right? Maybe variety matters more than amount of things within the task, right? You don't need to solve math problems 1 million times, right? For a model to understand how to solve math problems. Yeah, this would be the general answer.
I also want to ask a bit about the RLHF part. Like logically speaking, if we compare like how good is it for like RLHF when we compare to yeah, as Johannes' presentation earlier, he mentioned about like other than from human, the feedback can also come from larger model and such. Like let's say if we use like Google Translate API for the feedback, like how does it compare to like human, like because logically speaking, the effort will be practically zero because like yeah, we're there's no human doing it, but like maybe the result is like less human-ish, like yeah.
So if I understand this, instead of having a person doing this feedback, to ask another model to.
Yeah, like already pre-existing universally acceptable model, like yeah, that's why I choose like example of like Google Translate or such.
So maybe then the universally acceptable model role is to evaluate, not to make data. That's actually what I meant in the presentation. So we evaluate with a larger language model, not to, how to say, not to be in the part of the training in some sort.
Yeah, so it also it doesn't replace the human factor in the RLHF part, is it?
But I think you could, if you want to, like, if you want this preference data or some scorings or so done by a model, you still can do it. But like in this case, because I focus on aligning, like in the end you need the end user. Otherwise, you have to trust whatever the LLM wants to do. Like if you want to bias your output to a particular case, then you need someone who is going to use it or who has to evaluate how to do it, like to give the feedback. And yeah, you could use another model, but then you are not necessarily doing whatever you want. It's like the model will learn how the other model will want. But there are words that where they just say instead of using a human, we are using another model to generate this data or this reward model and use it to improving. But to me, I think it's a bit. I mean, maybe for improving can work, but if you want to align to your personal use case, then ideally you need to give the feedback yourself. That's if I understand.
In my opinion, like we fine-tune the model, eventually it will be used for human. So we must like ask human in the process to evaluate it finally. But maybe like larger evaluation with larger language model is like, oh, I train 20 models with different hyperparameters and I cannot like ask human, it will take forever. Maybe I can reduce it to 5 or 3. And after that, I will ask human. So that's usually the part of the process when you automate evaluation. And there's, I give you one example where evaluating with a larger language model is not ideal. Let's say I ask the large language model, you prefer A or B? And then the model answer with A. And then when I ask you prefer B or A, it's the same thing, but in different order. It will answer B. So there is a selection bias. Whatever you say first, it will just answer that, the first one. Not because it's better, just because you say it earlier. So that's one of the bias of evaluating with language model.
I see. Okay. Yep.